All right, guys, more on simple linear regression. So essentially the title of this could be what's behind the scenes in calculating beta 1 and beta 0. Well, guys, it turns out that to calculate beta 1, we have to create something called kind of the sum of squares between x and y and the sum of squares for x. Now, these formulas are a little insane. And I like to make these calculations using Excel, which I'll demonstrate with you. We had a data set before, and I'm just going to write it up here just in case you, it's been a while since well, you should have this in your notes if you're doing what you need to do. So we had 137 and 210, 15, I think. I think that's right. So we'll illustrate that here. But guys, the sum of squares between x and y can be found by taking the sum from I equal 1 to n. And guys, n is just the number of measurements that we've collected. In this case, there'd be 3 measurements. We have 2 measurements on the first person, 2 on the second, and 2 on the third. So we have a sample size of 3. And we would take the product of x and y minus, this is kind of the, if I can remember, we would take the, from I equal 1 to n, we would take the sum of the x's times I equal 1 to n, the sum of the y's, and we would divide by n. Now, I chose a small samples set for a reason, because these are really easy to create there. So, guys, if I multiply these out, this is saying that I need to multiply x and y. This is telling me I need to sum up these products. So when I have x times y, I have 1 times 2, and 3 times 10, and 7 times 15. So guys, when I sum those up, it looks like I get 137. Now right here I'm going to put the sum of the x's, so this is going to be 11. And the sum of the y's is going to be 27. And my sample size, of course, is 3. So guys, put that in your calculator. That's the beauty of a small data set. And so we get 137 minus, 11 times 27 divided by 3. So I get 38. All right, keep that on the back burner. Now the next thing we need to do is look at the sum of squares for the x value. And this can be found a couple of different ways. Probably the most straightforward way is from I equal 1 to n. Just take the difference in the x's and their means and square it. Now we get into a little weirdness here because you know, some of these are 11 divided by 3 doesn't turn out to be a nice, neat number. So there is an alternative form. And that's found by taking from I equal 1 to n the x's squared. So sum those up minus the sum of the x's sub i's quantity squared over n. Now, a lot of students will look at that and they'll think it's the same thing, but it's not. This is saying that because of order operations, this tells us that we have to square our x's before adding, and this says we sum up our x's and then square that value. And I think it'll become a little bit clearer as we work through it. So first thing here, I need to square these values, so I'm just going to come over here and square these. So 1 squared is 1, 3 squared is 9, and 7 squared is 49. So if my mental arithmetic is correct, that would be 59. Versus this value, this is the sum of the x of i's, and then square that. So 11 times 11 is 121. Guys, we have 3 objects, 3 measurements, so we take 121 divided by 3. So 121 divided by 3, and then take 59 minus that answer, So we get 18.66666. So let's just call it 18.67, rounded to 3 places. So guys, our B sub 1 is going to be 38 over 18.667. So guys, when I put that in my calculator, I get 2.036. And if you remember from the previous video, that should look very familiar because that was our slope. So, assuming that these measurements were collected from a population, so this is a sample, so these 3 measurements were collected from a bigger population, our best estimate of beta 1, which would be the slope of the relationship between x's and y's, all the x's and y's in a population, our best estimate of this slope is 2.036. Now, it turns out that the intercept is a lot easier to find. Let me get my paper separated here. Our intercept, B0, is just the mean for y minus the slope times the mean for x. So guys, the mean for y is going to be 2 plus 10 plus 15 divided by 3, which is 9, minus our B1, times our slope. So our slope is 11 divided by 3, which is 3.667. Yeah, as long as we don't do something goofy, make sure you remember you have to multiply before you subtract. So we're going to take 9 minus the product of 2.036 times 3.667. So we get 1.534. Which is, within some reasonable rounding. I think we got 1.536, if my memory serves me correctly, from the previous video. But again, it gives you an illustration of how we calculate these things using sum of squares. Now, one more thing. I intended to keep this video super short because the next one's going to be pretty insane. Let's revisit this residual analysis. And essentially, what does this do for us? And again, I covered this last week, but it's important enough to be redundant here. When I create my x's and y's, I can use my model to create my residuals. And guys, again, my residuals are what? They're my observed value minus my predicted value. I can look at the relationship or the scatter plot of the residuals over x. So in the residual analysis, I kind of ignore the y, and because residuals can be positive and negative, because guys, again, if I'm back to my x and my y relationship, and I have these measurements that I've collected, the line of best fit will go down the central focus, kind of down the center of them is a way to think about it, even though it's not technically correct. These values below the line have an observed value that's less than the predicted value, so their residuals are going to be negative. These values here have an observed value that's higher than the predicted value. These residuals are going to be positive. These residuals will be negative. Now, if our residual plot, so that's why we put the room for the negative residuals and the positive residuals, and instead of drawing our rectangular coordinate system that's all in the first quadrant, we look at the first and the fourth quadrant, because again, residuals can be positive and they can be negative, but they're over our x values. So guys, if we go back to our original data set, we had x's of 1, 3, and 7. So let's say we have 5 and 10. So we have 1, 3, and 7 as our x values. If we go back to our residuals, we can see that the first residual is negative 1.57. So let's write that down there. So we have x and y, 1, 3, 7, 2, 10, 15. And our residuals are negative 1.57. And guys, I'm writing this down so we'll have it when we get over there. 2.36 and negative 0.79. All right, let's go back to this. So I've written those down here. The way the residual plot will work is we go to the x value, which is approximately 1, which would be about right there. And let's have these at 3 and negative 3 when we sketch our plot. 1, the value when x is equal to 1 goes to a residual of negative 1.57, which would be about right there someplace. 3, which would be about right here, has a residual of positive 2.36, which would be right there. And 7, which would be about right here, has a residual of negative 0.79. Now, this is a very non-interesting and non-entertaining residual plot because we only have 3 values. But what will happen is we'll typically get a residual plot that will look like this. This. Or that. Now, what does this tell us? First of all, it addresses whether a linear model is appropriate for describing the relationship between x and y. But it tells us more. Guys, the assumptions for creating a linear model are this. First of all, we have to have linearity. Second thing, we have to have independence. The third thing, we have to have normality. And the final thing is we have to have equal variances. When we have a residual plot that looks like this, we can assume all of these are met. When we have a residual plot that looks like this, linearity is not met. And when we have a residual plot that looks like this, equal variances are not met. Equal variances just say no matter what the x value is, the spread in the residuals is about the same. Guys, the spread in the residuals right there is a lot different than the spread in the residuals for that x value. So we can't assume equal variances when we get this fanning approach in our residuals. Guys, I could go on and on about teaching residual plots, but I want to keep it as basic as possible. And I think by these 3 illustrations, I mean, okay, at the end of the day, let me just set forth my expectations here. If we can get these 3 examples down and know that this is a violation of equal variances, this is a violation of linearity, and this means that all of these assumptions over here have been satisfied, then I'm doing cartwheels. I'm in well, I don't know about cartwheels. I don't want to get hurt or anything, but I'm good. All right, gang, that's all I got. Take care.